Good day everyone, especially to my STEM 12 students. I am your Sir John Maricilibio, a senior high school teacher from Iloilo City National High School. Today I will be creating one of the several videos. This is to help you or to assist you in learning physics. I hope you will learn, support and subscribe this channel. General Physics 1. So this is the subject that you are taking right now, and we will base our topics on the most essential learning competencies identified by the Department of Education. So for content standard here, you're expected as a learner to demonstrate understanding of the following. Okay, so to start with, of course, we are expecting the official module from the Department of Education. However, I've tried to create some additional support. This is to further enhance your learning in physics. Okay, but of course, before we tackle all this, we need to focus first on measurement. That's why one of the most essential learning competency that you're supposed to learn is, of course, to solve some measurement problems involving conversion of units. So of course it's expected that at the end of this you'll be able to convert units or the expression of measurements in scientific notation. So we'll be dealing also with scientific notation, but of course we'll focus first on measurement. Okay, this will be our first topic before we deal with scientific notation and errors in measurement. We'll discuss first measurement and conversion of units. Okay, so of course we will study first measurement. So we'll define what is measurement, and later on we'll proceed to conversion topics and all topics that are expected to be covered in this competency. Okay, so we all know that all natural phenomenon, things that are happening, are actually following or they obey certain physical laws. And one of the primary goals of physics research is to discover these laws in physics. Okay, so it has been known for a very long time that the laws of physics are usually expressed in terms of mathematics. So we all know that mathematics are considered to be tools in physics. So physics and mathematics are closely related. So it is said that when you're good in physics, of course it's expected that you're also good in mathematics, because mathematics is considered to be one of the major tools in learning physics and in teaching physics. So usually physicists are also mathematicians. As a matter of fact, Isaac Newton, one of the leading physicists, is also a mathematician. He is the one who have contributed a lot in the development of calculus. So that's the relationship between physics and mathematics. So physics utilizes mathematics as one of its major tools to understand natural phenomenon. Okay, so we are dealing with physical quantities here, or a physical quantity. So any number that is used to describe a physical phenomenon quantitatively is called physical quantity. So we use a quantitative approach to describe a physical phenomenon. So that's how we define a physical quantity. So we will be dealing more with some of the physical quantities later on. Okay, so when we say measurement, how do we define it? So others may consider this as the process. So it is a process of comparing an unknown quantity. So we have something that is unknown to us, and we try to compare that with something that is already established, or this is already known. So we call this known quantity to be standard. So we try to compare something that is unknown with something that is standard. So that's why we have measurement. So for example, we don't know how long a particular object is, but we can compare that with something that is already known. So for example, a known 1 meter. So the standard 1 meter is compared to the length of something that is unknown. So that is a process called measurement. Okay, so measurement could also be process, or it refers to the determination or size or magnitude of something. So these are other definition that we can probably consider. No? So we try to determine the size, how big, how small, or the magnitude of something. Okay. Next, we will be dealing with the system of units. Okay, of course, we have mentioned a while ago that there has to be a standard. There should be a standard, I mean, for us to determine the magnitude of something that is unknown. So that's why they try to develop this what we call system of units. Okay, so prior to the development of standard units, we are all aware that our ancestors probably, or our forefathers, have used their body parts to utilize them, or the body parts, in measurement. So it usually depends on how we use them in our daily life. Therefore, we try to consider, for example, our fingers in measurement, our foot, our steps, before the system was established. However, they try to vary from country to country. So the use of body parts before were dependent on how they use them, and it varied from one country to the other. Okay, so that's why because of the use of body parts, there are some inconsistencies because of the fact that of course some legs are longer than others. Okay, fingers of one person might be longer from the finger of the other person. So because of this fact, there are inconsistencies, and for that reason, the call for the establishment of certain standards of units and measurements is really significant. Okay, so one of the system that was developed was the English system. So the English system is also known as the foot pound second system, so FPS system. So English system, of course, from the word English, it is directly denoted that this system was also linked to the old imperial or the UK system, which was originally defined in terms of yard for length, pound, and the gallon, and is believed to have originated in London. Okay, so this is the idea that we have learned from this system of measurement. Okay, so this system is mostly adopted by American systems. Americans use this, and since American colonized Philippines, so of course we are familiar with this, no? As a matter of fact, some of our carpenters are using the system. Let's say when they say board feet or board foot, so they are somewhat attributed to this English system. However, since the Mendenhall Order of 1893, the US pound and yard units have been defined in terms of metric unit of length and mass. So later they tried to adapt some other metric systems, no, and tried to modify the English system that they have adapted from the English system. These are some of the drawbacks that this system have. First, it's very complicated, or it's the complexity in converting one unit to the other. So it's very complicated if we use this system. Next, the differences between American units and British units. So some units may have certain differences. For example, the ounce, for both weight and liquid capacity are somewhat having some slight differences. Okay, so the existence of three different system of weights. No? So we have here identified these systems. Okay, for weights. which is different from the American compared to the English system. Okay, so other systems of measurement that were developed was this metric system. Okay, of course we are familiar with this. Metric system is a decimal system of physical units based on the unit of length meter, which came from the Greek word metron, which means to measure. So when we hear the word meter, it came from a Greek word which literally means to measure. Okay, so it was introduced and adopted by law in France. So we are all aware that this system was developed from originated in France in year 1790. So it was adopted as the common system of weights and measure by most countries. So most countries nowadays are adopting this kind of system. So especially for scientific work, then the system of measurement plays a very important role. Okay. Next, there is another system, the SI system and units. Okay, in 1964, this group, the Sistema International de Unities, abbreviated as the SI, is a system developed by the General Conference on the Bureau of Weights and Measures. So they tried, some of the experts in measurement or scientists tried to meet and adopted this system. Okay, so there are 7 fundamental or base units established on this system of measurement. As a matter of fact, this SI system is largely based on metric system. Probably we can say that the SI system is a sort of an improved metric system. Okay. So SI units are summarized as what we have mentioned, based mostly on the properties of earth and of water. So originally these are the definition that they've developed based on properties of earth and of water. So the meter was originally defined as this, so 1/10 the distance from the equator of North Pole, okay, along the latitude passing through Paris. Okay, this is in France. Okay, the kilogram, which was defined as the mass of this certain amount of water, 0.0001 cubic meter of water. Okay, the second was originally defined as 1/86,400 length of one day, or usually they considered one rotation of the earth. So this was their first definition of a second. Okay, so the definition of the ampere is for electricity, the amount of current. The definition of ampere is related to the electrical properties, okay, ultimately relating to the meter, kilogram, and second. So this is the ampere, the original definition. Okay, the Kelvin was defined in terms of thermodynamics properties of water as well as its absolute zero. The candela was defined by the luminous properties of molten tungsten and the behavior of human eye. So as what I've said, this is the original definition of the system of measurement. So we also have mole, which was defined by the density of carbon-12 nucleus. So this was how they originally developed the 7 fundamental units. Okay, however, over time, this system of measurement was redefined to become more precise. Okay, so because the need for precision is really considered by the scientists. So most recently, on May 2019, there were some major definition of the definition of SI units, in which the definitions of kilograms, ampere, Kelvin, and mole were all changed. Okay, so the following are the fundamental characteristics of the SI units. Okay, so they are not deducible from each other. So meaning we cannot obtain unit which is, say for example, meter from a second. They are entirely different quantity. Say for example, the ampere could not be deducted by combining meter, the unit of length. Okay, so next, they are invariant, meaning they does not change in time and place, especially in the classical context. Next, they can be accurately reproduced, so meaning we can replicate them, and the replication is said to be accurate. Okay, so they describe human physical world. Okay, so these are the characteristics or features of the fundamental units. Okay, these are the 7 fundamental units and their recent definition and examples. Okay, so the first one is length. Of course, the symbol is L. Usually we use L. In some books, they may use letter S, not to denote length side. Okay, however, usually we see L. Okay, the unit that we usually use is meter, M. Okay, small letter M, it has no period. This is the unit for length. The unit appears to be like a signature, meaning you can readily identify that we are talking about length when it is being trailed by a unit meter. So for example, when you have 10 meters or 10 m, this is the symbol for meters, we are dealing with length. So meaning we are trying to describe how long we are dealing with the length. So the length is the quantity, physical quantity, and the unit is, of course, meter. Okay, so when you see 10 m, it refers to the length. Okay, at present, now the meter is now defined to be the distance of light in vacuum travels in 1/299,792,458 seconds. This one is actually the speed of light in vacuum. So it's around about 3 times 10 to the power of 8 meter per second. That's the speed of light. So if you divide this over 1 second, over this of the second, then you will obtain the length 1 meter. So that's how long 1 meter is. This is the standard 1 meter at present. Okay, next quantity, we have the mass. Another physical quantity is mass. Of course, the symbol is small letter m, and the unit is kilogram. So kg, small letter k is small letter g. There is no period. So for example, when we say 5 kilogram, then we have 5 kg. We're talking about the mass. However, there are misconceptions at present. They interchangeably considered kilogram to be weight. However, when we say kilogram, it is supposed to be attributed to mass. However, because probably of it's widely becoming popular, they are still using kilogram as their mass, no? But however, kilogram should be attributed to the mass, and the weight should carry with it a unit which is Newton. Okay, however, we will be dealing with that more as we go on with our lesson. Okay, so at present, this is now how we define kilogram. It was redefined, and it's based on the Planck's constant, used in quantum mechanics to be exactly equal to this. No? Originally, they tried to consider the alloy of iridium and platinum iridium, no? Cylinder kept in Sevres, France. However, at present, this is now the standard and the most recent definition for 1 kilogram. So it's already now based on Planck's constant. Okay, third, we have the time. No, so of course, time, the symbol is letter T and the unit is second. Okay, or small letter S is the unit, no, for quantity. Of course, when you say 15 seconds, then we have 15s. So it refers to the time, how long or the time elapsed. No, so that's referring to the time as another fundamental quantity. Okay, at present, this is how they obtain the standard definition for time. So the second is now defined to be the duration of 9,192,631,770 period of radiation, corresponding to the transmission between two hyperfine levels of ground state of cesium-133 atom. So at present, that is how they define the time. Okay, next we have the electric current. Of course, the symbol is letter I and the unit is ampere, capital letter A. Okay, so when we say 1 ampere or 1A, of course we're talking about the amount of current. Okay, current are the something to do with the amount of charges that is passing per unit time in a particular conductor. So ampere is its unit, so current. So this is a constant current that when maintained in a straight parallel conductors of infinite length of negligible circular cross-section and are placed 1 meter apart in a vacuum, will produce these conductors a force equal to this amount of force, no, which is 2 times 10 to the power of 7 Newton per meter of length. Okay, however, in 2019 there are redefinition, and this ampere is now defined in terms of the elementary charge of electron, which is equal to this value, 1.602176634 times 10 to the power of 19 ampere second. So this is already adjusted based to this elementary charge. So that's the changes that they've made recently in 2019. Okay, next fundamental quantity, we have the temperature. Of course, the symbol is letter T for temperature, but of course unit is Kelvin. So you can say that you're dealing with a temperature if the unit attached is Kelvin. So the unit is Kelvin. So we say 20 Kelvin, 20 K, of course you are talking about temperature. Okay, of course there are other units which are Celsius and Fahrenheit. However, for SI system, Kelvin is used. Okay, how do we define Kelvin? How was it determined? So it is a fraction of 1/273.16, the thermodynamic temperature of the triple point of water. So this is the basis. However, at present, Kelvin was now redefined based on the Boltzmann constant, which was already set at this value. So 1.380649 times 10 to the power of 23. So this is the Boltzmann constant, in which the temperature Kelvin was now redefined. Okay, so there are changes already. Okay, next we have the quantity luminous intensity. Of course, we can sub L sub intensity. We are referring to luminous intensity. Of course, other may use letter I for intensity. However, we can have other symbol for this for each unit. However, the unit is candela. Of course, when you hear the word candela or CD attached to a particular value, let's say 35 candela, 35 CD, of course, we are referring to the brightness of the light, no? So we're talking about the luminous intensity. So candela is the unit that measures the brightness of light, and as somewhat carries with it a complex definition that includes a model of the response of the human eye to light of the different wavelengths. Okay, so that's candela. Okay, so those are some quantities, and the last of the list, of course, the amount of substance. I choose letter N sub S. Those are the amount of substance. Usually we use mole or MOL to denote this amount of substance. Usually we're familiar with this, especially when we're dealing with chemistry. Okay, so for example, when we have 5 moles, okay, 5 mol, okay, we're referring to the amount of substance. Okay, so those are some of the 7 fundamental quantities. And of course, this amount of substance, which contains as many elementary entities as there are atoms in 0.012 kilogram of carbon-12. So carbon-12 would be the basis in determining the amount of substance. Okay, 1 mole. However, in 2019, there is a redefinition by considering or by resetting the value of the Avogadro's constant, which is exactly to be equal to 6.02214076 times 10 to the power of 23 mole. So there is already a redefinition as far as the number of, or the Avogadro's constant is concerned. It was already set to this. So the new mole was defined based on this new redefinition of the Avogadro's constant. Okay, so to summarize, by the way, one of the reasons why SI prefixes was largely favored by most scientists is because of the fact that those fundamental quantities could be attached to a prefix. Okay, so we call that as SI prefixes. So this prefix provides a new meaning that will enable us to express a very large or a very small number. Okay, so these are some prefixes that are used in their corresponding value. So say for example, iota prefix, when attached to a fundamental unit, will provide with its new meaning. So iota, which symbolized by capital letter Y, when attached to a fundamental quantity, will have a new meaning. No? It will have a new value, which correspond to a particular powers of 10. So in this case, when we say iota, it's 1 times 10 to the power of 24. Okay, for zeta, okay, we have 1 times 10 to the power of 21. The symbol is capital letter Z. For exa, we have 1 times 10 to the power of 18, symbolized by capital letter E. Okay, of course, we have peta. These are all positive. These are a huge number. 10 to the power of 15, symbolized by capital letter P. Tera. You're familiar with this, no? In the word terabytes, it's somewhat 10 to the power of 12. So the symbol is capital letter T. So for giga, of course, 10 to the power of positive 9, symbol is capital letter G. For mega, of course, we have 1 times 10 to the power of 6. It's something to do with million. So the symbol is capital letter M. For kilo, of course, we have 10 to the power of 3. We have small letter K, which is the symbol. So you will notice that when it comes to kilo, it's start wherein the symbol becomes small letter K. Next, we have hecto. We have 100. HA is the symbol. Okay. For values to be smaller, then we have these prefixes also for very small numbers. Then we use centi. It's 10 to the power of negative 2. Small letter C is the symbol. Milli, 10 to the power of negative 3. Small letter M is the symbol. Micro is 10 to the power of negative 6. The symbol is mu. It's like letter U and like letter reverse of letter N. So mu, this is a symbol. Nano is 1 times 10 to the power of negative 9. Letter N, small letter N is the symbol. Pico is 10 to the power of negative 12. Okay, symbolized by small letter P. Femto, we have 1 times 10 to the power of negative 15. Letter F is the symbol. Atto is 1 times 10 to the power of negative 18. It's small letter A. Zepto, okay, negative 21. 10 to the power of negative 21, so it's small letter Z. Okay, and yocto, this very small. 10 to the power of negative 24, it's small letter Y, which is this symbol. prefix. So when we say prefix, we could attach that in front of our fundamental unit. Okay, say for example, if we have 20 kilometers, so when we say kilo is a prefix, this is being attached to a unit meter. So of course, when we're talking about meter, we're dealing with a quantity length. Okay, so we can say length is 20 kilometers. So the kilo once again is prefix, and this is the symbol 20, K for kilo prefix, and the SI unit meter, kilometer. So you can short-handedly write 20 kilometers to be 20 km, K for kilo and M for meters. Now notice that the prefix kilo was added to the SI unit meter. Next, okay, so when we say 20 kilometers, then we have 20, and kilo now could be transformed into a particular value. Kilo is something to do with 1 times 10 to the power of 3, as what I have presented to you, and we have SI unit meters. So when we say 20 kilometers, it's equal to 20 times 10 to the power of 3 meters. So 20 times 10 to the power of 3 is like 20 times 1000. So it has 4 zeros. So it's 20,000 meters. So when we say 20 kilometers, it's something to do with 20,000 meters. Okay, that's the meaning of that. So that's the effect when we attach prefix to a particular SI unit. Okay, another one. So for example, we use micro. So we have, let's see what will happen if instead of kilo, we'll have micro. So we have 20 micro, which is the prefix, plus seconds. We have 20 microseconds. So the symbol for micro is mu, and we attach the symbol for seconds as 20 microseconds. Of course, by looking at the unit, we can say that we're dealing with time. Okay, because second is the unit of time. Now, notice the prefix micro added to the SI unit seconds. So the particular prefix has a particular value based on our base 10. Of course, if you will recall on our presentation a while ago, where when we say 20 microseconds, micro has something to do with 10 to the power of negative 6. So we'll have 20 times 10 to the power of negative 6. So negative 6 implies that we need to move 6 places back from the decimal point. If this is the decimal point, we move 6 places backward. So of course, from this, so we'll be adding 4 zeros. Okay, so this 1, 2, here 3, 4, 5, 6. Of course, this will be the result. So later, our calculation will be faster if we'll be dealing later on with scientific notation. Okay, however, this is an example of how SI units are utilizing prefixes to express a very small or a very large number. They're using scientific notation to make the conversion faster, easy, and convenient. You will notice also that if we are using English system, dealing with a huge number like this would be difficult. However, in the SI system, because of these prefixes, conversion of units had become more easy and convenient. Okay, so I hope you have learned something about the prefixes used in measurement. Okay, next, as expected also in our competency, we need to convert units. So by considering the University of Physics, a book, University of Physics, by Sears and Szymanski, which I will be presenting later on the in the references. Now, it's adapted from their appendix that they have. But anyway, these are very common. These are already familiar. All of us are aware of this. But just to recap and to give you an overview, these are some of the common conversion factors that will be useful later on. I hope that as a student in physics, you will learn this by heart, because some of you later on might have a chance or will be dealing with conversion of units. So for example, you will later on become engineer and you need to convert meters into centimeter. Some of you might become nurses later on, that you need to convert liters into milliliters. Okay, some of you will become scientists probably. Now, it's very important to deal with the conversion of units. As a matter of fact, you cannot succeed in physics if you will have difficulty later on in converting one unit to the other. So I encourage you students to try learning or mastering the conversion of units. Of course, at present there are a lot of applications that allows us to convert units easily. However, it's still very important for us to know the concept behind the conversion of units. Okay, so these are some conversion of units from length 1 meter. Kilometers could be converted into miles. So what you can see, a mile is probably longer than a kilometer, because 1 kilometer is just simply this 0.6214 of a mile. And of course, when we say meter, 1000 meters is equal to 1 kilometer. As what you can see also, a meter could be converted into other units like the English system into foot or inches. Okay, centimeter could be converted also into inches. Inch. Okay, you will notice that the inch is bigger than centimeter. So 1 centimeter is just simply 0.3937 inch. Okay, so these are some of the sample conversion units that you can find in some books. As what I mentioned, I've adapted this from the University of Physics. Okay, these are also some of the units that are later on useful in terms of area. Then the unit is centimeter squared. Okay, and you can convert this into a particular inch squared. You can use this conversion factor also. Okay, 1 meter squared is equal to 10,000 centimeters squared. Okay, 10 to the power of 4. Okay, or 10 times 10 times 10 times 10. Okay, 4 zeros. Of course, then it's 10,000. Okay, which could also be converted into square foot. Okay, volume could be converted into gallons, liters. Okay, force could be converted into pounds, dyne. So more likely, when we say weight is actually a force, a downward force. That's why if we say your weight is expressed in terms of poundal force, like this, it's more accurate to say that your weight is expressed in pounds rather than expressing that in terms of kilogram. So it's even safer to use pound as your weight. It's more correct than the use of kilogram. Okay, so time, we have minutes, seconds, days to seconds, year to seconds. Okay, those are some values which are available on some references. Pressure, energy, you'll notice from joule to calorie. So these are units. So we can determine that this is pressure because of the unit EA. Bar, pounds per inch squared. These are units that helps us identify that we are talking about pressure. The Newton, the pound, the dyne, these are indicators that we are dealing with force. Area, which is inch squared, centimeter squared. The dimension of length squared is actually dealing with area. That's why if a length is measured in inch and you have the square inch of that, that's referring to the area. If you measure that in terms of centimeter, the length multiplied to the width, which is also in centimeter, producing centimeter squared, then we are dealing with area. Okay, for volume, it's cubic. However, we can convert those things in terms of liters. Okay, so those are some ideas that we can use later on when we convert. So these are very important conversion factors that you can also memorize by heart. However, if it's difficult for you students, probably during our examinations, it's also possible that this table will be provided, to facilitate your solving. Okay. So here are other conversion factors. In terms of angle, we have radians or pi radians over 180, revolution or the RPM, revolution per minute, in terms of radians per second. So things like that. We are dealing with angle. So we can also have speed in terms of meter per second to be converted into foot per second. Foot per second into meter per second. Okay, so miles per minute into miles per hour. Okay, so power in terms of watts and joules per seconds. So these are some of the conversion factors that we may find useful later on as we convert. Okay, however, in our competency, we're expected to learn how to convert units. So conversion of units is one of the emphasized competency that you must learn in physics. Now, how do we convert units? Of course, we are usually confronted with a given bearing with it a particular unit. So a given with a particular unit. And of course, what's expected is we are asked to convert this to the desired unit. So we are expected to have an answer with a desired unit. So when we say conversion, we are not affecting the value of the original given, and we wish that our final answer will carry with it a converted unit that we desire, or the desired unit. Now to do this, we need a conversion factor. It is in such a way that it has a desired unit at the upper portion and a given unit at the bottom. The purpose of that is so that when we multiply that with our given, this unit will eventually be cancelled, leaving only the desired unit. Okay, so if you will notice the desired unit divided by a given unit and has a particular value is considered to be a conversion factor. If you divide the value of this conversion factor, it's just simply equal to 1. Okay, because they are just the same. So multiplying number by 1 will be itself. We are not changing the value. However, we might change the unit and we are not affecting the original value of the given unit. That's the principle behind conversion. So this is actually the format. Okay, therefore, when we have a given multiplied, when a given is multiplied to this conversion factor, the value remains the same. And of course, as what I mentioned, its equivalent value and unit is obtained. So that's the thing that we are hoping to achieve in conversion of units. And of course, our most essential learning competency is expecting us to perform this. Okay, so say for example, we have here given 30,000 centimeters. We wish to convert that into meters. Okay, from this value, centimeter into meter. Of course, to solve for this, we need to refer to the conversion table that we have, or by common sense, we can say 1 meter is equal to 100 centimeter. Okay, so what you can see, these are based on what's given and what's asked. So what's given is in terms of centimeter and what's asked is in terms of meter. So for that reason, we need to establish a relationship between meter and centimeter. Okay, and we have here 1 meter is equal to 100 centimeter, or in symbol, then we have 100 centimeter is equal to 1 meter. Now if we follow the process, we write the given, We have the given, and we multiply that to a conversion factor. This is our conversion factor wherein 1 meter is simply equal to 100 centimeter. Since they are equal, if we divide 1 meter with 100 centimeter, of course this is equal to 1, right? Okay, you will notice also that the unit that we desire, which is meter, is placed above, for the purpose that when we multiply 30,000 to this, and eventually dividing this to the bottom part, the centimeter unit will be cancelled. Okay, so if we have 30,000 centimeter multiplied to 1 meter, what's left later on when we operate this will be meter. Okay, multiplying this, dividing, we remove 2 zeros, what's left will be 300. Okay, it's equal to 300 meter. So that's how we convert a unit from centimeter into meter. So the desired unit was once again obtained, which is meter, while the centimeter unit is cancelled on the process. So once again, when we multiply that in a fraction, we multiply the numerator, which is this, and divide that with the denominator. By doing this, once again, centimeter is cancelled, leaving only meter. Okay, I hope that this example is useful for you. Next example. Okay, example number 2, we have now the English system. Okay, for our English system, of course, we have this one. For example, one wants to determine how many inches are there in 5 feet. Okay, you will notice that this system of measurement are in English system. Okay, they are not our SI system, because in SI system we are using meter for length. Okay, the same solution is to be employed. First, we look for a conversion factor that would link what is asked. So what is asked is in terms of inches, and what is given. This is the information to obtain. What's given is 5 feet. Okay, in this case we have feet and inches. Wherein, by looking at our table, we can say 12 inches is equal to 1 foot. Okay, so this is the conversion factor that we have. So if we follow our process before, then we can have 5 feet. This is our given. We multiply that to our conversion factor in such a way that what we desire is above. So we are trying to look for inches in our final answer. So we have 12 inches, this one, and divided 1 foot. You will notice that they are equal. If we divide the 2, then this is equal to 1. And multiplying this given to 1 will be itself. However, by doing this, we can replace feet by inches. So we multiply to the numerator, 5 times 12, which is 60, divided by 1 foot. You'll notice that this feet, okay, will be cancelled, eventually leaving inches. So what's the result? We have 60 inches, where the desired unit was obtained. We're looking for inches, and while the given unit, which is in feet, was cancelled, because we multiply to the numerator and divide this to the denominator, obtaining this final answer. Okay, so that's example number 2, the conversion of units. Next, example number 3, we have the English to metric system. Okay, so for example, we have to convert 3,600 feet into meters. You will notice that feet is a metric system, English system I mean, and meters is the metric system. Okay, or SI system also is in meters. Okay, so that's it. So to solve for this, first we have to look for a conversion factor that would give us a link between what's asked and what's given. So what's asked is in terms of meter, and what's given is in terms of feet. Okay, in this case, feet, which is the English system unit, and meter, which is the SI system unit, could be established wherein we can say that 1 meter is equal to 3.28 feet. Okay, so because of this conversion factor, we can once again follow the process. We write the given, 3,600 feet. We multiply that to a conversion factor. Once again, 1 meter divided by 3.28 feet is actually this one, which is just equal to 1. Any number multiplied to 1 will be itself. However, by doing this, we can eliminate the unit feet. Okay, by multiplying this here and dividing it here at the bottom. So the result is 1097.26 meter, where the desired unit, which is meter, was obtained, while the given unit, which is in feet, was eventually cancelled in the process. That's how we work with conversion from English to metric system. As what you can see, class, the pattern is repeated. No, I would like to emphasize, I would like you to consider the pattern. Which is very simple. No, just consider what's given, what's asked, and repeat the pattern. Okay, next, example number 4. So we will now be converting, but this time we will involve the prefixes that we have. Okay, so for example, 500 kilogram. We'd like to convert this into megagram. Capital letter M is a prefix for mega. You will notice that these are grams. It simply means that we are dealing with mass in this case. Okay, to solve for this, we look for a conversion factor that would link what is asked and what is given. However, in this case, no, this is not an ordinary case because there are already prefixes. Further steps should be considered. Okay, so for beginners, no, it's very important first that for students like you, it must be converted to its base unit first before converting to the desired unit. Now, we would like to express kilogram into grams first, and from gram we can go to megagram. So for students like you who are just beginning to understand this, we'll try to convert this first into gram, and then eventually from gram we'll be converting that into megagram. So let's do the process. So we all know that 1000 grams is equal to 1 kilogram. So we can directly convert 500 kilogram into grams. So you will notice I've emphasized here that it's very important to convert this into the base unit first. Okay, meaning we would like to convert kilogram into gram first, and we convert that to the desired unit later on. Okay, let's see. However, we can also say mega is 10 to the power of 6 or 1 million. Okay, the prefix kilo and mega have their value attached with base unit gram. Okay, now we follow the process. Let's say 500 kilogram, we convert that into gram. We have 1000 grams and 1 kilogram. We use this. Okay, so we have here 500,000 grams. The given was expressed in base unit. Okay, you'll notice kilogram was cancelled. This is already expressed in grams. So the next step is to convert that to the desired unit. Okay, so we have here 500,000 grams. 1 megagram is, okay, I'm glad that it's already corrected, 1 million grams. Okay, 1 million grams is 1 megagram. Okay, you will notice that the gram, the base unit, is not replaced. Mega is replaced by a value, a number. So bear that in mind. Mega means million, 1 million grams, 1 megagram. And eventually, by doing this, from our base unit grams, we multiply that to the numerator, the 500,000. Look at how many zeros, 1, 2, 3, 4, 5. Okay, look at this, 1, 2, 3, 4, 5, 6. Okay, of course, we need to just move one decimal place when we're dividing. And eventually, we divide this using our calculator, and we end up with 0.5 megagram. You will notice that the desired unit here is megagram. So 500 kilogram is equal to 0.5 megagram. So that's the idea. With the knowledge of interpretation later on, these things will become more handy and more easy for you. But once again, now if we use prefixes, we need to convert to the base unit first and eventually obtain the desired unit by following the same process. Okay, however, if you are expert later on, then you can just simply combine all of this and still obtain this value. Okay, but for the meantime, I want you to consider the principle behind determining the desired unit, in dealing with conversion involving the SI of prefixes. Okay. So next we will be dealing with conversion involving powers. Okay, so for example, an area which is 60 meters squared, would like to convert this into centimeters squared. Okay, you will notice that this involves power. Okay, they are units, but they have power. Okay, to solve for this, we look for a conversion factor that will link what's asked and what is given. Okay, since what we could easily remember is this conversion, we say 1 meter is equal to 100 centimeters. Then we can derive out of this the relationship between meter squared and centimeter squared. Okay, we can say 1 meter is equal to 100 centimeter. By squaring all of them, we are not actually affecting their value. They will still be the same if we square all of them. So we'll obtain a conversion factor in which we can say 1 meter squared, this one, is equal to 100 times 100. This will give us 1 with 4 zeros, or it's 10,000 centimeters squared. Okay, so what you can see, distributing the square, no? Okay, so and eventually by using the process, since we already have a conversion factor, so we write the given 60 meters squared. We multiply that to a conversion factor in such a way that we would like to eliminate meters squared and come up with centimeters squared. Eventually, multiplying 60 by this will result to this. Okay, so that's how we convert units involving power. Okay. The desired unit was obtained. Of course, we are trying to look for meter squared, and of course centimeter squared and meter squared was cancelled here on the process. Okay, next we have another one is still involve power. How about in cube? We have 60 centimeter cube into inch cube, cubic inch. Okay, so like what we did earlier, we look for a conversion factor that would link what's asked and what is given. Okay, since we all know that 1 inch is equal to 2.54 centimeter, we can derive a conversion factor relating to inch cube to centimeter cube. How do we do this? Of course, we have this, and then we cube all of them. So 1 cube, inch cube, okay, will result to 1 inch cube. Okay, we distribute the cube to 1 to inch, so we have here 1 cubic inch. Next we have cube of 2.54. 2.54 times 2.54 times 2.54 will give us 16.39, and centimeter when cube was centimeter cube or cubic centimeter. Notice that the value 2.54 is multiplied 3 times to produce this. Okay, now we follow the process. We write again the given, these are given, multiplied into the obtained conversion factor. We have 1 inch, 1 cubic inch, divided by 16.39 centimeter cube. Eventually will produce this result, where the desired unit was obtained while the given unit in centimeter cube was cancelled. Okay, so this is how we produce the conversion factor, or how we perform the conversion of units in terms of if it involves unit power. Okay, next, conversion involving multiple units. Say for example, this is the unit of speed, wherein we combine the unit of kilometer per hour into meter per seconds. Now to solution, Of course, we use the same approach, the same principle. We look for a conversion factor that would link what's asked and what is given. This is what's given and this is what's asked. Okay, we can say 1 kilometer is equal to 1000 meter. And we could also say 1 hour is equal to 3600 seconds. Because of these conversion factors, it's possible for us to convert all of this. Okay, we follow the process. We write the given 60 km per hour. We multiply that to a first conversion factor in such a way that kilometers will be removed and meters will be left. Okay, all numerators will be multiplied. So we have 60 times 1000 times 1 hour. Now in this case, we make a conversion factor in such a way that hours will later on be cancelled and seconds will be left. So you notice seconds is at the bottom. So you multiply all numerators and divide that to the denominator, which is 3600. It will produce 16.67. Now you will notice all of these units were cancelled. Now what's left is the unit meter divided by the unit seconds. So we can say that 60 km per hour is equal to 16.67 meter per seconds, where once again our desired unit, which is meter per second, was obtained. We have it here, and the given unit, kilometer and hour, in this case, was eventually cancelled. So that's how simple it is. So class, I hope that you will practice. You may assign other values here and try to practice solving, converting units that are involving multiple units here. In this case, example number 6. Okay, next, example number 7. This is temperature conversion. Of course, this is familiar later on when we deal with the heat, thermodynamics, and other topic. And I know that you're already familiar with this in your chemistry class. So to change temperature from degrees Celsius to Kelvin, so if you wish to look for the value in Kelvin, then if you have a value in degrees Celsius, just add to 73, you'll obtain the value in Kelvin. Change the temperature in degree Fahrenheit to Celsius, then you'll use this formula. Now if the Fahrenheit is given, subtract that with 32 degrees, multiply that to 5 and divide that to 9, you'll obtain its value in degrees. To change the temperature in degrees Celsius to Fahrenheit, then you'll use this formula. To change temperature in Kelvin to degrees Celsius, this formula could be used. To change temperature in degrees Fahrenheit to degrees Rankine, then we have this. By the way, Rankine is another unit for temperature. Okay, to change temperature from Rankine to Fahrenheit, then we have this. To change temperature in Rankine to degrees Celsius, we have this. To change temperature from Kelvin to Fahrenheit, we have this formula. To change temperature Kelvin to degrees Rankine, then we have this formula. Okay, and so on. So where F here is the Fahrenheit scale, C for Celsius scale, K for Kelvin scale, and R for the Rankine scale. Okay, so those are some ideas about temperature. I will not dig deeper into this because I know that you are already familiar with this on your chemistry, and you will still have your chemistry class not to deal with this. However, these are very basic. Now, so for example, once again, if Rankine is given, just substitute this, perform the operation, and you'll obtain its temperature in Kelvin. Okay, so if you have any questions later on, you may just shoot some questions in our classroom, Google Classroom, to address those problems. Okay, by the way, I have prepared some sample worksheets for you to work on conversion of units, because it's just an overview of what your worksheet will look like, and one of the worksheets I prepared, it has a competency, because this competency is really required for us to cover. I hope that given this assignment later on for you to work on, you can convert, say for example, from 5,000 meters, convert that into centimeter, and all these other values. You apply the knowledge that I've taught you, mass, area, speed, time, and up to temperature later on. Okay, so good luck, guys. So by the way, for reference, I've used this reference. Okay, in CRT, Shams outline, the workbook developed by Dr. Rabi, module by Shadwick, Physics for K-12 by Singh, General Physics 1 Mechanics by Simpson, Physics for Scientists and Engineers by Jean Collins Survey. This is one of the very significant book that I am using, the University of Physics 12th edition by Sears and Zemansky, Shom's outline on Turing problems of physics engineering uh, in science by Brown. Okay, so good luck, guys. I hope this helps you in working with your first assignment on measurement and conversion of units. So if you have any questions later on, I will be answering that through our stream, and I hope that you will subscribe and try to wait for some additional videos that I will be posting. This is to support you in learning General Physics 1. Keep safe, God bless, and I hope that you will benefit from this video. Thank you, and God bless once again.